All right, let's talk about a chemical that, well, you've definitely smelled it, but you've probably never given it a second thought. Ammonia. You know, that sharp, pungent odor. But its story? Oh, it's incredible. It's a story of pure genius, some serious moral questions, and, well, the survival of billions of us. So let's dive in.
Okay, I'm going to start with just a number. 45%. What do you think that is? Go on, take a guess. Is it the amount of ammonia in Windex? Nope. Maybe how much is in our air? Not even close. The answer is honestly so much bigger, and it's something that props up our entire modern world.
Yeah, you heard that right. Almost half of all the food grown on this planet today is only possible because we figured out how to make ammonia from scratch. Without it, there's just no way we could feed our current global population. It is, and this is no exaggeration, the chemical that literally feeds the world. So why is that?
Well, it all starts with this huge problem in biology. See, plants, the very foundation of our food chain, are desperate for nitrogen to grow. And you might think, well, the air is almost 80% nitrogen, what's the big deal? The problem is that nitrogen in the air, N2, is incredibly stable. Its atoms are locked together so tightly, plants just can't use it. It's like being thirsty in the middle of a saltwater ocean. For centuries, our only option was natural stuff, like manure, but that was never going to be enough for a booming population. We had to find a way to crack the nitrogen code.
And the key to that code was ammonia. Chemical formula, NH₃. It's such a simple little thing. One nitrogen atom bonded to 3 hydrogen atoms. If we could just make this molecule, we could give plants nitrogen in a form they could actually use. The massive challenge, though, was figuring out how to force that stubborn nitrogen from the air to react with hydrogen. And the person who finally cracked it, well, he's one of the most complicated figures in all of history.
So, let's meet Fritz Haber, a German chemist whose work would change the 20th century in 2, let's just say, profoundly different ways. He was the brilliant mind who finally figured out how to create ammonia pretty much out of thin air, a discovery that would earn him the biggest prize in all of science.
I mean, Haber's career was a rocket ship. He became a professor at the super prestigious University of Berlin, made his world-changing discovery, and yep, in 1918 he got the Nobel Prize for it. But there's a really dark side to his story. Because during World War I, that same Nobel laureate became the head of Germany's chemical weapons program.
And this just lays it all out, the jarring contradiction of Fritz Haber. On one hand, his work on fertilizer is credited with saving, literally, billions of people from starving. On the other hand, he's known as the father of chemical warfare, for developing poison gas as a weapon. His legacy really forces you to ask some tough questions about science and its power for both good and evil.
So, how did he actually do it? How did Haber manage to do what nature does, but on this massive industrial scale? The answer is in the method he cooked up, which another guy, Carl Bosch, later scaled up for factories. We now call it the Haber-Bosch process. Let's pop the hood and see how it works.
This is the heart of it all, the chemical equation. You take 1 molecule of nitrogen gas, mix it with 3 molecules of hydrogen gas, and you get 2 molecules of ammonia. But see those double arrows in the middle? That's the tricky part. It means the reaction can go backward. The ammonia can just break apart again into nitrogen and hydrogen. So the real game isn't just making the reaction happen, it's forcing it to the right and keeping it there.
To figure this puzzle out, chemists used a really neat concept called Le Chatelier's principle. You can think of it like a seesaw. The principle basically says that if you mess with one side of a balanced chemical reaction, say by changing the pressure or the temperature, the reaction will shift to the other side to try and get back in balance. So Haber used this idea to, well, basically bully the reaction into making more and more ammonia.
So here are the 3 big tricks he used. First, tons of pressure. He squeezed the gases together at hundreds of times normal atmospheric pressure. That physically shoves the molecules closer together, making them way more likely to react. Second, temperature. Now this one's a balancing act. Heat makes the reaction go faster, which is good, but the reaction itself creates heat, so too much warmth actually pushes it backward. The sweet spot is right around 450 degrees Celsius. And finally, the secret sauce, a catalyst, in this case, iron. A catalyst is like a chemical matchmaker. It gets the nitrogen and hydrogen together, speeds up the whole process, but doesn't get used up itself.
And here's what that looks like in a real factory. First, you get your ingredients, nitrogen from the air, hydrogen from water. Then you compress them a lot. Next, you blast them into a super hot, high-pressure reactor with that iron catalyst. Now, only about 15% of it actually turns into ammonia on the first try. But here's the genius part, you cool the whole mixture down. Ammonia turns into a liquid way before the other gases do, so you can just drain it right off. And what about the leftover nitrogen and hydrogen? You just shoot them right back to the beginning to go through the process again. It's this continuous, super efficient loop.
The invention of this process over 100 years ago completely reshaped our planet, but its impact actually goes way beyond the farm. It's a key ingredient in so much of our modern world.
So no big surprise here, farming is still king. A massive 70% of all the ammonia we make today goes straight into producing fertilizers. That is the #1 legacy of Haber's breakthrough.
And that 70%? It brings us full circle, right back to the beginning. It's used to make key fertilizers like urea, and that in turn is what supports the 45% of the world's food supply we were talking about. The entire modern food system is built on this one chemical process.
But what about that other 30%? Well, it turns out ammonia is a real chemical jack of all trades. It's in the cleaner you use on your windows, it's the refrigerant gas that keeps your food cold, it's used to kill microbes in food processing, to adjust pH levels in fermentation, to cut down on pollution from diesel engines. It's even used as rocket fuel. It's this invisible workhorse of our entire society. So from the dinner on our tables to the rockets flying to space, ammonia is just this cornerstone of modern life, all springing from the mind of one of history's most complicated people. It solved the great challenge of the last century, how to feed everyone. And now, as we look to the future, a lot of people are asking if this same simple molecule could help us solve the biggest challenge of our time, the hunt for clean, sustainable fuel. It's a question that pretty much guarantees the story of ammonia is far from over.